Hi everyone, this is Mrs. J. Today we're going to talk about transformations and characteristics of quadratic functions. I have a quick warm up for you, so please pause the video and give it a try. Alright, so since we are focusing on quadratic functions this chapter, we're always going to start by looking at that parent function, which you can always make by just creating a little table of values here. So we see that we have that parabolic shape. This graph is called a parabola. There are some key features. Here we have the vertex, which for our parent function will be at the origin. Our domain is all real numbers. Our range is 0 to infinity. And our graph is always positive except at 0 at the vertex, so make sure you don't include that. And our parent function is never negative. You can see that it's increasing to the right of our vertex and is decreasing to the left of our vertex. The x and y intercept are the same in this case, both at 0. And we do have an absolute minimum here at the origin. Please note that our vertex will always be the absolute max or min when we're working with quadratic functions and these parabolas. And then last, our axis of symmetry, which is the line symmetry that exists with these types of functions. So you can see if I drew this vertical line here at x equals 0, our graph is symmetrical. If I folded my paper on this line, it would map onto itself. So this axis of symmetry can be really useful for us because if we know some points to the right of our graph, we can simply reflect them over our axis onto the left. And please note that that axis of symmetry will always go through your vertex. So it's essentially going to be the x value of our vertex. There is one more kind of key feature to quadratic functions that I want to talk about, which I'll come back to later in the lesson, but it's this vertical growth pattern that all quadratic functions follow. So if you look at the vertical distance between this coordinate and this coordinate, which is 1 unit to the right, this vertical distance is 1. Now if you look one more unit to the right here, this vertical distance between the coordinates is 3. And then if you look at the vertical distance between your next two coordinates, which would be from here to here, you see that that distance is 5. So hopefully you're seeing a pattern. If you did the vertical distance to the next coordinate to the right, it would be 7 and then 9 and 11. So this vertical growth pattern, we can definitely use it to help us graph our functions a little bit easier. Now this could change if we have some type of stretch or shrink, but we'll talk about how to do that later on in the lesson. But again, when you see or when you hear me say that vertical growth pattern of 1, 3, 5, that's what I mean. And it is just a pattern that all quadratic functions follow. So if there is a pattern, we are going to use it because usually that will make our job easier. And again, that would just continue on 1, 3, 5, 7, 9, so on and so forth. So here we're going to do a quick overview of the different transformations we talked about last unit. Here it's just specific to quadratic functions. However, it's the same rules that we would apply to any type of function we're going to work with this year. So here f of x is just our parent function x squared. So remember, if we add or subtract to our x value specifically, it's going to be a horizontal translation, which is essentially a shift to the left or to the right. And remember, when it says minus h, it's actually shifting to the right. And when it says plus h, it's actually shifting to the left. Now, if we add or subtract a value outside of our function, so see it's not specifically grouped with x, that's going to be a vertical translation, which is just going to be a shift down or up k units. So if k is positive, it's going to shift up. If k is negative, it's going to shift down. Then we have our reflections, which is essentially multiplying by a negative. So if we have a negative out front, that is going to be a vertical reflection, and that always will go over the x-axis. And then if we multiply our x specifically, that becomes a horizontal reflection, and that would be over the y-axis. Now this one's kind of an interesting case because if we're multiplying the x value by a negative and then we go to simplify it, if you square a negative, it becomes positive. So for these types of functions, that reflection over the y-axis actually doesn't change our graph, so it's essentially just the same as x squared. And then our last type of transformation were those dilations, or what we would call stretches or shrinks. Now, here you can see that we are multiplying specifically 2x. It's grouped within the parentheses. And remember, this one did have that kind of tricky rule. We do need to remember that the stretch or shrink factor was always by a factor of 1 over a. So whatever you see in the function, the stretch or shrink factor is actually the reciprocal of that. So if a is between 0 and 1, when you take the reciprocal of that, it's going to be greater than 1. So that's when we have a stretch. And if a is less or greater than 1, when you take the reciprocal of that, it's going to be less than 1. So we call that a shrink. So think about what your factor is and then determine if it's a stretch or shrink. And do just be careful with that. So notice here, when a is greater than 1, we actually have that shrink factor. So you can see it's like I put my hands on the left and right and just kind of move them in. And then when a is between 0 and 1, the reciprocal gives us that stretch factor, which actually makes our graph stretch out or it makes it wider. Now here as another stretch and shrink, but this time you can see that the a is not specifically grouped. I understand these look very similar, but the parentheses do matter. So here this would be considered a vertical stretch or shrink, and it is just by a factor of a. So if a is greater than 1, it's a stretch, and if a is between 0 and 1, it's a shrink. And notice that a is always going to be positive because if there's a negative, that's a different type of transformation. That would be our reflections. All right, so we're going to do a little bit of review of what we learned last unit and see if we can describe the transformations of f of x in reference to our parent function, which is just x squared. So if you look at this first example, example A, see a couple different things here. The first thing I notice is out front we have a negative, so that is going to be a reflection, and it's a vertical reflection, so that's over the x-axis. And then I also see that a factor being multiplied out front. It is not specifically grouped with x, so that's going to make it vertical. So this is a vertical shrink, and it's a shrink because the factor is less than 1. So we'd say by a factor of 2/3. Then in here we see that we are adding for specifically 2x. Since it's being done to x, that makes it horizontal. Adding or subtracting makes it a translation. Remember, this will move in the opposite direction, so this will actually move to the left 4 units. And then we see that adding and subtracting outside of our function or after the x is grouped, so this is going to be a vertical translation. And this one will go in the direction you think. It's going to go down 1 unit. So hopefully looking at this example, it feels like a review from last unit. And if it doesn't, maybe we need to go back to the videos from last unit and rewatch some of those. Because again, these are the transformation rules we learn at the beginning of the year, and we apply them to every new function that we encounter. Now for part B, there is a tricky step here that we have to remember. So when we have a vertical or a horizontal stretch or shrink or a reflection, in addition to a translation, we need to make sure they're separate. We actually need to factor out the -2. We need to separate it. So that's the first thing I need to do. So within the things that are being squared, we would have -2 times x minus 3. All of that is still being squared. All I did was I separated it out, factored it out of our binomial, okay? And then we still have the +7 on the outside. Now from here, we can choose to leave our function like this. So I'm going to talk about 2 different ways we can approach this. And then we can describe the different transformations from here. So one thing, we can start with that 3 out front, which would be a vertical stretch by a factor of 3. And then I'm going to move to this value that's being multiplied. So the negative, since it's within the stuff being squared, it's being done to x. That's a horizontal reflection, which is always going to be a reflection over the y-axis. and then this is going to be a horizontal stretch or shrink. Since the stretch or shrink factor is 1 over 2, it's always the reciprocal of A, this is going to be a shrink. So this would be a horizontal shrink by a factor of 1/2. And then we have the horizontal translation, and it's going to go to the right 3. So remember, this will always move in the opposite direction. This moves in the direction that you think. This will be a vertical translation up 7. Now it's completely fine to do this, but you'll see this is a ton of transformations to work with. So for some functions, and this will work for our quadratic functions, there may be ways for us to simplify a little more. So I can actually square the negative and the 2 and then move it out front. So we can actually simplify this function. So 2 squared is 4, negative 1 squared is positive 1. So just that positive 4 is just going to multiply out front. So we have 12 times x minus 3 squared plus 7. Okay, so we can simplify this a little bit more and then describe the transformations, which is probably a little bit easier for us to do, because then we just have a vertical stretch by a factor of 12, and then we still have those translations to the right 3 and up 7. So these translations are the same, but in simplifying what's inside our larger brackets, we were able to kind of reduce the number of transformations. So again, either way is completely fine, but I would recommend simplifying your function as much as you can before you go on to describe transformations or graph or anything like that. So there's our quick little overview of describing transformations, which we learned about last unit. All right, so now we're going to practice writing transformed quadratic functions. So here it says, let g of x be a vertical stretch by a factor of 2 and a reflection over the x-axis, followed by a translation 3 units down of this function, f of x equals x squared. So since we kind of have two different steps of transformations, I'm actually going to transform this in 2 steps. So I'm going to call this intermediate function h of x. And for h of x, I'm going to start with those first ones that they mentioned, the vertical stretch by a factor of 2, and then that reflection over the x-axis. So those are both vertical reflections. So we're just going to essentially do negative 2 times f of x. So here's that reflection over the x-axis. Here's the vertical stretch. So I'm just going to multiply my original function by negative 2. So h of x equals negative 2 x squared. But then it says followed by, so I'm going to do that as a second step. And this one we're going to do the translation 3 units down. So we're actually going to transform h of x now. So g of x, and again, this is another horizontal, or it's a vertical change because it's 3 units down. So it's going to be done to the outside of our function. So it's going to be h of x minus 3. So I'm essentially going to take h of x, which is negative 2x squared, and I'm going to subtract 3. So I know this looks like something that you could have done in one step, and maybe you can, but we do need to be careful that we are doing these transformations in the correct order. And it is kind of nice to be able to split it up and describe the transformations in that function format, because as these problems get a little trickier, I think it will make the problems easier to work with. So let's look at part B, which is a little bit trickier. It says, let g of x be a translation 3 units right and 2 units up. So it's going to be the first round of transformations. But then it says, followed by a reflection over the y-axis. And notice this time we're actually transforming a function that is no longer just x squared. It's x squared minus 5x. So I'm going to do this in 2 steps again. I'm going to call h of x that first round of transformations. So since it's a translation 3 units right, that would be f of x minus 3. That would transform f of x 3 units to the right and then 2 units up. So then plus 2. So this is essentially saying wherever I see an x, or wherever I did see an x, I'm going to replace it with x minus 3, and then at the very end, I'm going to add 2. So h of x would be x minus 3 squared minus 5 times x minus 3, and then I add that plus 2 after. So notice everywhere I saw an x, I replaced it with x minus 3. So I'm going to expand this out a little bit. So here we would have x squared minus 6x plus 9 minus 5x plus 15 plus 2. And then we can just combine like terms to simplify our intermediate step. All right, so now we have to look at that second round of transformations, which was a reflection over the y-axis. So that transformation is actually a horizontal transformation. So we can now call it g of x. So g of x is going to be h of negative x. So that would create that reflection over the y-axis. So then I'm going to go back to here, and I'm going to replace every x with a negative x. So g of x equals negative x squared minus 11 times negative x plus 26, and then I am going to simplify. We know that negative x squared just becomes positive x squared, and then here we would have plus 11x, and then that constant will still say positive. So here you go. So here it is important that we have done these transformations in 2 separate rounds. So you do need to watch out for if there's a specific way they say to apply the transformations, or if there's an order to it. And I do recommend showing out those 2 steps and kind of using that function notation to help you along the way. All right, I've got one for you to try on your own, so please pause the video and give it a shot. All right, go ahead and check your work here. So since there were kind of these 2 different rounds of transformations, I did this in 2 steps. So my intermediate one I called h of x. So notice I did f of x plus 4 minus 1. So I replaced all of my x's with x plus 4's, and then I subtracted 1 after. Then I expanded this out, combined like terms, and I have that first round. And then I need to reflect it over the y-axis. So that would be taking h of x and multiplying the x by negative 1. So g of x is h of negative x. So notice I replaced all of my x's with negative x, and then I simplified to get my final answer. All right, so now we're going to look at a few different forms of quadratic functions that we're going to encounter. The first one is called vertex form. So vertex form should look pretty familiar. It looks like a transformational form. It's when your equation says y equals a times x minus h squared plus k. So we call this vertex form because it's really easy to see what the vertex is. The vertex is always going to be hk. Notice this says negative h, so that implies that this is an opposite value. Now this a value out front, which would be our vertical stretch or shrink factor, is going to be really useful for us. And it can help us find what I like to call a vertical growth pattern. So remember in the warm-up, we kind of talked about that vertical growth pattern from our parent function, which was 1, 3, 5, which was the vertical distance to the next coordinate 1 unit to the right. Now you can simply adjust this vertical growth pattern according to this a value by multiplying the 1, 3, 5 by that a value. And that will apply the stretch or shrink, and if there's a negative, you can do that as well to apply the reflection. And then one more thing we're going to start to look at is what's called the axis of symmetry. It's always going to be a vertical line that goes right through your vertex, so it'll be x equals h, the x value of your vertex. Axis of symmetry can be nice because if we know points to the right of the axis of symmetry, we can reflect and automatically find points to the left. So I just want to look at these 2 examples really quick. So if you look at this first graph, look where our vertex is right here. It's at negative 5, negative 3. So notice here we have x plus 5 and then the minus 3. So it's negative 5, negative 3 would be our vertex. Write that in. And then if you look here, we have an a value of 1/2. So that means our vertical growth pattern should be adjusted. So I'm going to multiply each of those by 1/2. So it's going to grow by 1/2, then 3/2, then 5/2. So if you look from my vertex, if I go up 1/2 over 1, that would be the next coordinate. And then from here, I go up 3/2 over 1. That gives us this coordinate. And then I would go up 5/2 over 1, and that gives us our next coordinate here. So that's how you can use that vertical growth pattern to help you plot a couple points to the right. And then we could reflect it over our axis of symmetry, which in this case is x equals -5. You simply reflect it over to find coordinates on the left. Now just another example here, you can see that the number out front is negative. So notice now we have a downward facing graph. We can see that our vertex should be at 310. Remember, this is always opposite, which it is. And then since we have that -2 out front for our vertical growth pattern, we'll do -2 times 135. So it'll be -2, -6, -10. So again, just to make sure we understand how we can utilize that, from our vertex, I would go down 2 over 1, and that's my next coordinate. And then from that coordinate, I would go down 6 over 1, and that's my next coordinate. And then from there, I could go down 10 over 1, and that's my next coordinate. So it just quickly allows me to find a couple additional coordinates to the right of our vertex, and then we can reflect it over our axis of symmetry to find coordinates on the left. An alternative to this, once you know where your vertex is, you could always make a table of values and plug in a couple x values to the right and the left. This vertical growth pattern just kind of saves us some time, and it's always good to look for patterns within different functions that we can utilize to help us graph or analyze our function. All right, let's try this one together. We're going to graph this function, and we're going to try to graph it from that vertex form. So one thing we notice here is that there is that coefficient in front of x. So we know to make it in vertex form, we do need to factor that out and then simplify. So I do need to do a couple steps before I start actually graphing. So I'm going to factor out the 1/2 within this binomial. So it's still going to be squared for now. So notice, again, it is still within the stuff that is being squared, but then to simplify it, I can actually just square it and move it out front. So 1/2 squared is 1/4, so I'm going to move that out front, and it leaves me with -2 times x plus 4 squared plus 5. So it is super, super important that our equation is in that vertex form, which looks like this, before we start working. So if you don't do that, you're going to have the wrong vertex, you're going to have the wrong a value, so sometimes you do need to do a little work before you start graphing. Now from here, we can see that our vertex should be at -4, 5, so you can start by plotting that. And then because we have that -2 out front, that is going to affect our vertical growth pattern. So our vertical growth pattern will be -2, -6, -10. Again, this is just kind of a trick to help us plot additional points. So from the vertex, I go down 2 over 1, and then down 6 over 1. And then if it fits on your graph, you could go down 10 over 1, but we'll just do as much as fits on our graph. So these 5 coordinates will be enough. And notice I just reflected this coordinate over my axis of symmetry, which would be x equals 4. I'm going to write AOS for axis of symmetry, and it's at x equals -4. So again, if you know points to the right of your vertex, you can use that axis of symmetry to help you find points to the left. And there you go. All right, go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work here. Please make sure you put it into that correct vertex form by factoring out the 3 and then squaring the 3 to simplify. So here you can see that our vertex is at 3, -8, and there is that vertical stretch by a factor of 9. So our vertical growth pattern is pretty stretched out. I can really only fit one coordinate to the right and left on our axis, and that's totally fine. And you can see that our axis of symmetry is this vertical line at x = 3. So once you know this point, you just reflect it to the other side. All right, so now we're going to look at another form that we're going to encounter quite a bit for quadratics, and that's called standard form. So standard form is when your equation says y = ax squared plus bx plus c. So for this one, you do need to do a little extra work to figure out what the vertex is. So there is a formula that you can memorize. The x value of your vertex is always going to be -b divided by 2 times a. So b is always the coefficient of x, and a is always the coefficient of x squared. And then to find the y value of vertex, you just simply plug that x value back into your function. So this should be something that you absolutely have memorized. So when your equation is in this form, you are going to need to know -b/2a to help you find that vertex. Now, that a value is going to be the same a value as it would be in the vertex form that we just covered. So you can still take that a value and use it to find your vertical growth pattern by multiplying it by the 135. And then for this form, it is actually really easy to see what our y-intercept is. It's always going to be at that c value, which is your constant. So remember, a y-intercept is when x is equal to 0, so these terms would disappear and you're just left with c. So it's not probably the most convenient form for graphing, but it is definitely doable as long as you know how to find that vertex. So here's kind of an example of if you have that positive a value, you'll have that upward facing parabola, and the x value of your vertex is at -b/2a. And then if you have that negative a value, it just makes a downward facing parabola. And notice here in both, your y-intercept is at that c value. So again, this is just a different form of our quadratic equation. All right, so let's give this next one a try together. So here you can see that our equation is in that standard form. So the first thing I'm going to want to do is find the x value of our vertex. And again, the formula is -b/2a. So I have negative, and I can see that my b value is also negative. And then I have divided by 2 times 3. So x is going to be +6/6. So the x value of our vertex is 1. And then we're going to simply plug that into our function to determine the y value of our vertex. So here we get -2. So our vertex is 1, -2. So we can start by plotting that here. And then I can look to my a value, which is 3, to help me determine my vertical growth pattern. So it's going to be a 3, 9, 15. So again, plot as much as you can fit on your graph. So from here, I go up 3/1. And then I go up 9/1. And then I could reflect that over my axis of symmetry, which again will always go through your vertex. And then I know I have a point here at 0, 1, and then -1, 10. And there you go. Another thing we can look at when our equation is in this form, again, is that y-intercept, which should always be at that c value. So it's just something to check for. We could see that our y-intercept is 0, 1, which is exactly what we would expect it to be. So that's another point, an easy point that you can always include. All right, I have one for you to try on your own, so please pause the video and give it a shot. All right, go ahead and check your work here. Our vertex should be at 4, -10. And then because of that a value out front, we do have a vertical shrink by a factor of 1/2. So our vertical growth pattern will be up 1/2/1, up 3/2/1, and then up 5/2 over 1. Another point that we know would be the y-intercept, which should be at 0, -2. And then I can reflect that over my axis of symmetry, which is x equals 4, to give us an additional point. So notice if I'm 1, 2, 3, 4 units to the left of my axis, I simply go 4 units to the right. So that's an additional point that we can add pretty easily. All right, the last form we're going to talk about today is called intercept form. And it looks like this: y equals a times x minus p times x minus q. So notice here that we have factors of binomials with x in them. So it's called intercept form because when it's in this form, it's actually really easy for us to determine the x-intercepts. They would be at p0 and q0. So notice here it says x minus p, and the x-intercept is at positive p0, so these are always going to be opposites. Whatever number you see inside your factor, the x-intercept will be at the opposite. Now, once you know your x-intercepts, you can use those to help you find your vertex, because your vertex, the x value of the vertex, is always going to be exactly halfway between your x-intercepts. So the way you find that halfway point, the way you find the halfway point between any two numbers is adding them together and dividing by 2. So if you add up p and q and you divide by 2, that should give you the x value of your vertex, and then you simply plug that into your function to find your y value. So again, your vertex is always going to be exactly halfway between your x intercepts, but then you do need to plug that value in to find what the y value of the vertex is. This a value out front is the same as all of the other a values. You can use it to help you adjust your vertical growth pattern in the same way that we've done with the previous two forms. All right, so let's give this one a try together. We can see that it is in that intercept form. So the first thing that I like to do is to list out what my x-intercepts are. So they're going to be at -3, 0 and at +1, 0. So to find that halfway point, I'm going to add them up and divide by 2. So I can see that my halfway point will be at -1. So that means my vertex is somewhere on the line x equals -1. So to figure out what my vertex is, I'm going to plug -1 back into my function. So I have -2 times -1 plus 3 times -1 minus 1. And we should get +8 here. So our vertex is at -1, 8. So right here. And then I can see that my a value here is -2. So I'm going to use that to help me adjust my vertical growth pattern. So we go down 2 over 1, down 6 over 1, down 10 over 1 from our vertex. So again, down 2 over 1. And we can reflect that over our axis of symmetry. Down 6 over 1, so that's good. It's hitting right where we think it should. And then from there, we could also go down 10 over 1 and then reflect that to our other side. And there you go. All right, here's one more for you to try on your own. So again, pause the video and give it a try. All right, go ahead and check your work here. Our x-intercepts should be at 4 and -2. The halfway point should be at x equals 1. So you can plug that back into your function to find your vertex, which is at 1, 3. And then we do have that a value of -1/3. So we'd go down 1/3 over 1, down 1 over 1, and then down 5/3 over 1, which hits our x-intercepts, which is a good sign that we graphed this correctly. All right, so now we're going to see if we can apply what we've learned today to a real-life problem. So here we have a parabola shown right here that shows the path of our first golf shot, where x represents the horizontal distance in yards and y is the corresponding height, also in yards. It says the path of our second shot is modeled by this function. So the graph is not shown, but we have the function. So we want to know two things: which shot travels farther before hitting the ground, and which shot travels higher. So if we want to figure out which shot travels farther before hitting the ground, we want to compare those x-intercepts. So here at 0, 0, we're assuming that's where the shot, where the ball starts. So you can see that this ball travels horizontally 100 yards before hitting the ground. And please note that when it says hitting the ground, we should interpret this to mean when y equals 0, which is another way of asking for an x-intercept. So to compare with our other function, we're going to want to figure out what the x-intercepts are here. And I know it doesn't look like it, but this is actually in that intercept form. Here's my a value. My first factor is just x minus 0. So my first x-intercept is actually 0. And you can see here that my second x-intercept is at 80. So for f of x, my x-intercepts are at 0, 0, and 80, 0. So you can see if you compare the two, this one travels 100 yards before it hits the ground. This one travels 80 yards before it hits the ground. So which shot travels farther before hitting the ground? That would be the first shot. So we say the first shot travels farther. And we could even say by 20 yards if we want to be even more specific, because this one travels 80, this one travels 100. Now when they ask which shot travels higher, well, we know that for a parabola, the absolute max or min will always occur at the vertex. So what they're asking us to compare here would be the y value of the vertex. And since we're looking for the height, again, that would be the y value. So we can see that this graph, or for this ball, the highest point it reaches is 25 yards. So that's the highest point for that first shot. So if we want to figure out for the second shot, we're going to need to find the vertex of f of x. So we can do that we can start by finding the x value of the vertex. So we want that halfway point. So it's going to be at 40, and then we can plug that in, f of 40, to find the y value of our vertex. Times 40 times 40 minus 80. So we can see the y value of our vertex would be 32. So our second shot travels 32 yards high. Our first shot travels 25 yards high, so the second shot travels higher. And again, if you want to be more specific, you could say by 7 yards. So for problems like this, we just need to be able to interpret what they are asking us to compare. Sometimes we're comparing y-intercepts, sometimes we're comparing x-intercepts, sometimes we're comparing parts of our vertex. So it's just important that you understand what the different parts of our quadratic functions would represent in a real-life scenario. All right, that is all for today's video. Thank you so much for watching.